So you probably know your way around an alkene, right? Carbon-carbon double bond, nice and flat, pretty straightforward stuff. But what happens when you decide to stick two double bonds right next to each other? Well, you get something a little weird, a little twisted. Today, we're diving headfirst into the wonderfully strange world of the allene. Okay, so let's just get a look at these two. On the left, you've got your standard ethylene. It's totally flat, like you could press it in a book. Simple. But then on the right, that's allene. And I know, it looks flat in that drawing, but trust me, that's just a disguise. It's hiding a really cool 3D secret. So what's the deal? Is it flat or is it twisted? And more importantly, why does that little twist matter so much? That's the big question we're going to unpack right now. To solve this little molecular mystery, we've got to start with the basics. What even is an allene? And that brings us to our first section, where we'll see that its classification as a cumulated diene is our first major clue. Right, so cumulated is really just a fancy way of saying the double bonds are stacked right on top of each other. Bam, bam, no space in between. This is totally different from the conjugated systems you're used to, where they're separated by a single bond. And this unique, consecutive arrangement, well, it's the source of everything weird and wonderful about this molecule. So, if the stacked double bonds are the culprit, where does the twist actually come from? Well, that brings us to our second section. And here's a hint. The secret isn't on the ends of the molecule. Nope. It's all happening right there in the middle, with that central carbon atom. That one atom is the key to this whole thing. Okay, you're going to want to pay close attention here, because this is where the magic happens. That central carbon is what we call sp hybridized, and it's forming two separate pi bonds. But here's the kicker, literally, the twist. Those two pi bonds can't lie in the same plane. They're forced to be perpendicular at a 90-degree angle to each other. So you can imagine one bond going up and down, and the other one going front to back, right through the screen. And here's the direct result of that weird orbital arrangement. Because those pi bonds are twisted at 90 degrees, the groups attached to the end carbons get locked into that same 90-degree twist. So the big number one takeaway here is that allene is absolutely not a flat molecule. It has a built-in twist right in its very structure. All right, now that we get the twist, we can get to the really fun part. For our third section, we're going to play a little game. I call it the symmetry game. We're going to start with a basic allene, and we'll start making little changes to see if we can break its symmetry and build something really special, a chiral molecule. So here's our starting player, just a plain old allene molecule with only hydrogens on the ends. Now, because of that 90-degree twist, you can actually slice this thing in half in two different ways and get a perfect reflection. Imagine one mirror plane cutting through the front hydrogens and another one cutting through the side ones. And this brings us to the first rule of the game. If a molecule has a plane of symmetry, it can't be chiral. It's like having a perfectly symmetrical face. Your reflection looks exactly like you. With two mirror planes, our allene is definitely 100% chiral. We haven't won the game just yet. Okay, time for our first move. Let's swap out one of those hydrogens for a chlorine atom. Now look closely. Hey, we did it. We just destroyed one of those mirror planes. But there's still one left. You can still slice the molecule right through that remaining CH and that new CCl bond. And as long as there's even one mirror plane left, it's game over. The molecule is still achiral. We're getting closer, for sure, but we're not quite there. We need a better move. This brings us to section 4 and to the final move in our game, the one that flips the whole board. We're about to see the exact arrangement that breaks all the rules of symmetry and finally gets us a win. And here it is. This is the winning move. The absolute key is that each end of the allene has to have two different groups attached to it. So on the left, you can't have two hydrogens. You need a hydrogen and a chlorine. And on the right, you can't have two hydrogens either. You need, say, a hydrogen and a bromine. It's this specific combination that seals the deal. So take a good look at this new molecule. Go on, try to slice it in your mind. Flip it, turn it, reflect it. Can you find any single plane that would create a perfect mirror image of the other half? You got it. There aren't any. They're all gone. By putting different groups on each end, we have completely obliterated all reflective symmetry. And a molecule that has no plane of symmetry is chiral. We've won the game. But wait a minute. This victory leads to a very strange question, which we'll explore in our fifth section. We just made a chiral molecule, but where's the chiral carbon? This leads us to a really cool and kind of mind-bending new type of chirality. I know what you're thinking because it's the first thing I thought too. It's a totally fair question. We spend all this time learning that chirality comes from a carbon with 4 different things attached. But if you look at our chiral allene, not a single one of its carbons fits that description. So what is going on? Well, the best way to think about it is to think about a simple screw. A screw is definitely chiral. It has a handedness, right? Righty-tighty, lefty-loosey. But a screw doesn't have a single chiral point. Its chirality, its handedness, exists along its entire length, its axis. Our allene is exactly the same. Its chirality isn't located at one specific atom, but is spread out along the molecule, making its mirror image a totally different, non-superimposable object. And there's a name for this. It's called axial chirality. Instead of a chiral center, the molecule has a chiral axis, an imaginary line running straight through those 3 carbons. The twisted arrangement of the groups around that axis is what gives the whole molecule its handedness. And this idea becomes incredibly important when you're designing complex 3D molecules like new medicines. All right, for our 6th and final section, let's boil all that theory down into a dead simple practical shortcut. This is how you can spot a chiral allene in just a few seconds, no problem. So here's the foolproof test. Just look at the 2 carbons on the ends of the double bonds. If either one of those carbons has 2 identical groups attached to it, like 2 hydrogens or 2 chlorines, boom, it's achiral. You can stop right there. But if the left end has 2 different groups and the right end has 2 different groups, then you've got yourself a chiral molecule. That's it. That's the whole trick. And that brings us to a final thought to chew on. Let's make the chain even longer. What about this molecule with 3 double bonds in a row? Think about the geometry we've just discussed. The first twist happens between the first and second carbons. What does that 3rd double bond do? Does it add another twist, or does it untwist it? Is this molecule flat or 3D? Chiral or achiral? I'll leave you with that one to ponder.